Sabina. Yeah, so it's a great pleasure to be here at this. I haven't been to ICMS in this new location. It was very nice where it was before, but this is very splendid. It's lovely to be here, and the weather is as beautiful as I remember it in Scotland. So this is a joint work with several colleagues. And when we started the work, we were all at Reading, but we've dispersed since then. So Raphael was with us as a Marie Curie Fellow. He's now has a permanent position in Kiel. Carl Michael Perfect is moved to Trondheim, but my colleague Yannick is still with us in Reading. Right. So what am I going to talk about today? So I'm going to talk about a conjecture, which I'm going to attribute to Carlos Koenig because it's in one of his books, on the spectral radius of the Neumann Poincaré or double layer operator on Lipschitz domains. And we got quite excited and thought we could probably produce a counterexample and prove it's not true. And then I'll talk to you about testing this conjecture. And I'll obviously talk about these things, but it's basically testing it by a combination of analysis and numerical analysis methods. Right. Let me say something about what this conjecture is to start with, and indeed what the Neumann Poincaré operator is, if you haven't worked on that. Let me just remind you what Lipschitz domain is to start with, and this is, I'm showing it in R squared because that's where I can draw the pictures easily. And basically, just locally in the neighborhood of every point X on the boundary, the boundary is locally the graph in some rotated coordinate system, the graph of a Lipschitz function with some Lipschitz constant L, which can be bigger than 1 in this talk. In fact, it would be important that it's really much bigger than 1. So these are not Lip1 domains. We don't like them. Importantly, kind of obviously this allows corners. So here this is a graph of a function where the slope is 1. Well, I do 0 on the left hand side, but then 1 where we've got the bumps. So this is a Lipschitz graph of a Lipschitz function with constant 1. So this is a Lip1 territory, I guess. It also allows, this will be important for us, it also allows infinitely many corners. So what am I doing here? I'm basically starting at a point here. I'm going up with slope 1 until I hit this dashed line. Then I'm coming down with slope 1, going up again, coming down, going up. And obviously that creates an infinitely many bumps. But the slope is never more than 1. So this Lipschitz constant is 1. Okay, so it's starting to look like I am doing Lip1 boundaries, but I'm not. So let's assume we've got a domain which is bounded in Lipschitz. So this notation here is point y on the boundary, ny is the unit normal pointing out to the domain, which is defined almost everywhere with respect to surface measure if you're Lipschitz. And then the double layer or Neumann Poincaré operator is given explicitly by this formula. So d by point x on the boundary gamma, x minus y dot ny. And we saw this quantity actually in the talk just before lunch, divided by mod x minus y to the power d, and then there's a constant here. So quite a simple kernel. And so I'm interested in the spectrum of this operator. So obviously it's set a lambda such that d minus lambda I is not invertible, and this is the spectrum as an operator on L2 gamma, and it's well known since the late 70s, early 80s that this d result, but this operator d is bounded in L2. Okay, and this is the conjecture. It's a conjecture about the spectral radius. So R of d, the maximum of mod z for z in the spectrum of d. Conjecture, that's an equal to R. Right, and so this was our aim in the project, to disprove this conjecture. by rigorous numerical analysis, including rigorous numerical integration and error estimates. The spoiler, we failed badly. We ended up, in fact, proving that the conjecture holds in new cases. So, which was disappointing, but and that's captured in this paper, and that's what I'm going to talk about in the rest of this talk. Right. Okay. Well, let me say something a bit more about it. Yeah.
Just a quick question. Why would we care?
Why would we care? That's a good question, and we approached it, to be honest. We started on this because it's a conjecture that's been made, and we thought we could disprove it. And that was on the basis of some related work that I'll talk about, which was to do with thinking not about the spectrum, but about the essential numerical range of the operator. And certainly the essential numerical range is very, very important for theory of convergence of Galerkin methods and things like that. So those results were definitely important. And then the examples we had there, we thought would disprove this. So there's an argument that L2 is not the sensible space to look at this. That a lot of the work on Neumann Poincaré operators and applications to things like quasi-static modelling of plasmonic stuff, which a number of people in the audience have worked on. So there, it's kind of natural to work in energy spaces, which are h plus or minus a half, depending on whether you're thinking about D or the Joule. And so the spectrum there is definitely relevant for practical applications, but it's less obvious what the importance of understanding the spectrum on L2.
What is the physical meaning of this operator?
So this is the double air potential operator. This arises naturally when you're solving Dirichlet problems for Laplace's equation. You get the operator equation to solve is half identity minus D. That's the operator. So half identity minus D times some density phi equals the Dirichlet data on the boundary. Or with other values of lambda, so lambda I minus D, that operator, lambda I minus D phi equals something, that arises in transmission problems. So modeling transmission problems where you've got Laplace equation outside and inside, and then you've got some jump conditions across the boundary. And there, classically, mod lambda bigger than half is of interest, but in applications in plasmonics where you've got sign jumping in the jump conditions, then also cases where mod lambda is less than half are also of interest.
And is it self-adjoint?
No, it's not self-adjoint except in the special case when gamma is the boundary of a sphere.
Is it such conjecture for Helmholtz? If you do, you add some smoothing part, right?
So if you start, okay, so this is also something I know quite a lot about, but yeah. But if you go to Helmholtz, then you can start getting the spectrum can be arbitrarily big as the wave number increases. Yeah. So this is something special to Laplace. Yeah.
Is the operator norm known for T? Or is the operator norm known at all?
I'm sorry, I couldn't hear what you said.
The operator norm of the operator?
Is the operator norm known? I'll say something about that in a little bit later. Yeah. Right. So anyway, well, why did people believe this conjecture? Well, first of all, if you're not interested in whole spectrum but just interested in eigenvalues, then the eigenvalues of the adjoint of this operator D are always in the interval minus a half to half, and that's the Green's theorem argument, which is an old one done for smooth boundaries in already by Kellogg, and it carries over to the Lipschitz case. If gamma is smooth, then an xy are on gamma, then x minus y is nearly orthogonal to the normal at x. So you've got this inequality. And that then means that the kernel of this k dashed, which is just the kernel we've already seen, but with roles of x and y reversed, satisfies that its modulus is less than equal to a constant times this power of x minus y. And so this is weakly singular. And of course, integral operators with weakly singular kernels are compact. So the spectrum then is just 0 and the eigenvalues, but the eigenvalues are between -1/2 and 1/2. And so, of course, the spectral radius is less than equal to 1/2.
Isn't it
In
really
that
singular without the smoothness?
No, it's strongly singular without the smoothness. Yeah.
It is less than dimension.
So in general, you just have mod x minus y here. So for example, if d was 2, so my d here is the dimension of the ambient space. So if we're in 2 dimensions, then you've got 1 here, but this is an integral around the boundary. So you've got 1 over mod x minus y. You're branching the boundary. Yeah,
sure.
And in fact, and this is much more delicate, that d dash is compact as soon as gamma is C1. Okay, so if you've got a C1 boundary, then this conjecture definitely holds. And going beyond C1 boundaries, so to going to more general Lipschitz boundaries, which might have corners, less than or equal to 1/2 is omega's convex. If omega has small enough Lipschitz constant, so maybe epsilon domains or something like that. If omega is a polyhedron, or a curvilinear polygon, so quite a lot of evidence. So why on earth did we think this conjecture might not be true? So that's the second part of my talk. And to explain this, it'd be helpful to have a reformulation of this conjecture. So because the eigenvalues of d dashed always lie in -1/2, it follows that the spectral radius less than or equal to 1/2 if and only if the essential spectral radius of d dashed is less than or equal to 1/2. And that's the one way of defining that is to say that's the infimum of the spectral radius of d dash plus k over all compact perturbations k. And actually, perhaps I just write on the board. So obviously this is kind of clear, and this is kind of clear in one direction, of course. That going from here, this is less than or equal to 1/2. Then obviously this is less than or equal to 1/2, and going in the other direction. So if RS d dash less than or equal to 1/2, then by definition, the definition I put up here, then that means that there exists a K compact such that R d dash K is less than or equal to 1/2. And of course, that implies that if we look at d dash plus k minus lambda I, and we take mod lambda bigger than 1/2, so we're beyond the spectral radius, and of course that's invertible. And of course, if we then cross out the k, then we still know that it's Fredholm of index 0 of mod lambda bigger than 1/2. And if it's Fredholm of index 0 and lambda is not an eigenvalue, then of course we know that it's invertible. But the eigenvalues are all between -1/2 and 1/2. I would get that minus lambda I is invertible. The mod lambda bigger than 1/2. In other words, the spectral radius of d dash is less than or equal to 1/2. Okay.
Do we also need to worry about eigenvalues of the adjoint operator, or are they always complex of?
So we don't have information about those, but if it's freedom of index 0 and lambda's not an eigenvalue of d dashed, then it's invertible. Yeah. Yeah, and the spectral radius of d, the same as spectral radius of d dashed, and the same is true for the essential spectral radius. So in other words, we've got this equivalence. So we can reformulate the conjecture as saying that the essential spectral radius of d less than or equal to half. Okay, and I'll also need to talk about essential norms. Of course, those are defined in a similar way. Essential norm of d, just the infimum of norm d plus k over all compact perturbations k. Okay, so why do you think this conjecture might not be true? Okay, well, one case where it is true is the case when we've got a curvilinear polygon. And then, in fact, the essential norm is the same as the essential spectral radius, and they're both equal to half. But what happens if we have infinitely many coordinates rather than a polygon with finitely many coordinates? So what I'm drawing here is so it's basically something which is kind of smooth. It's at least C1 here, and then on the top it's the graph of something of some Lipschitz function. And what Lipschitz function is it? Well, it's one which has one bump of slope L, and then two smaller bumps also of slope L, three smaller bumps of slope L, and obviously they're getting smaller and smaller, so we're fitting in infinitely many bumps of slope L. And this was a particular geometry that I studied in an early paper with you and Spence, and we could make some explicit computations to show that the essential norm of D for this particular geometry, this particular the double layer operator on this particular gamma is greater than or equal to L over 2. And if you're interested in essential numerical ranges, and I know a number of people in the audience are there, and also we could also show the essential numerical range contains the disk of radius L over 4. Okay, so when we came to think about this conjecture, this then kind of made us excited. So the essential norm obviously is going to infinity as L increases. Essential numerical ranges containing larger and larger disks. So surely this essential spectral radius will also tend to infinity as L tends to infinity. Okay, and so we set off then to compute that and see what happened. So this is the next section of my talk. The kind of right. So to make things a little bit easier for ourselves, we smoothed off the corners. So we've got lots of oscillations here, like we had, but we've smoothed these off. But the same arguments again show that the essential norm tends to infinity as the slope tends to infinity. And in fact, for this particular example, we can compute the essential norm is bigger than 0.817. And okay, so then we set off to compute how big is the essential spectral radius. Is it greater than a half? And sadly, so there was a lot of excitement as we did these computations. And sadly, the answer was no. And let me show you what we're computing here. So I'm just drawing a circle centered on the origin, radius a half. And I'm then plotting the essential spectrum of the double layer operator on this particular boundary. And that's those black curves here. So I'm saying the essential spectrum, in fact, it's an approximation to the essential spectrum. I'll talk to you about how we're computing that. But one thing which is apparent is that the whole of this essential spectrum is contained in this circle of radius a half. And of course, the essential the essential spectral radius is also, I've written one characterization of it, but it's also the maximum of mod lambda over lambda in the essential spectrum. So visually, we can see here that is less than a half.
No, it is not compact, this operator there.
This, no, absolutely not. No, it's not. No, it's not compact.
Because of that point over there.
Yeah, because of this point. Yeah. So if, for example, if you had something like this, if you had a Lipschitz boundary with a single point, then it would not be compact because of this single point. You'd have some continuous spectrum, and this is even worse. This point, what's happening in the neighbourhood of that is considerably worse than if you've got just a straight line meeting in a point.
Did you say something about polygons, right? So you.
Yes, I did.
For polygons.
No, absolutely not. It's compact when you've got C1 boundary.
C1, okay.
Yeah, but once you go to polygons, then you've lost compactness. Yeah. Right. So okay. So the remaining thing I'm going to talk to you about is how do we compute this essential spectrum of D? And this is only approximation, and visually looking at it, it looks like the essential spectral radius is less than a half. Looks like this is all contained in. But how do we kind of rigorously prove that the essential spectral radius is less than a half? Okay, so I'm only going to do this for a specific class of boundaries, and it's a class of boundaries that I'm going to call locally dilation invariant. So this is just a term we've made up. And what it means is that at each x on the boundary, either the boundary is locally C1, or it coincides locally with what we'll call gamma subscript x, where x is the point we're looking at, which is a dilation invariant graph, meaning that if we take gamma x, multiply it by some alpha, then we recover gamma x again. So if it was a wedge here, if it was just two straight lines, then this would be true for every alpha, every positive alpha. But now we're just going to insist that this is true for some alpha in the range 0 to 1. So this example is locally dilation invariant. It's locally C1 at every x, except for this particular x, where it can coincide locally for this particular value of alpha with the graph of this function, f of s mod s sine squared pi log to the base alpha of mod s. And the important thing about that formula is it implies that f of alpha s is the same as alpha times f of s. And that's equivalent to gamma x having this dilation invariance property. Okay, so how do we calculate this essential spectrum? So the first step is a localization step. So let capital X denote the set of X at which B holds. So we don't have to worry about the points where it's locally C1, just about the points where it's locally, the graph, it locally coincides with the dilation invariant graph. And in fact, there can only ever be finitely many of these points. So this X here is a finite set. So then the essential spectrum of D, this is the localization formula, is the union over this finite set of points X of the spectrum of dx, where dx here just denotes the Neumann Poincaré operator, but where we're integrating over this infinite graph gamma x. So gamma x here is the graph of a function. In this particular case, the gamma x is the graph of this function f with s going from minus infinity to plus infinity. Okay, so this reduces it just to calculating what the spectrum is for these dilation invariant graphs. And so I'll say something about that. And it's a little bit easier to explain just in the 2D case. And when gamma is a half graph, in other words, when gamma is with s, just with s greater than or equal to 0 here, rather than s going from minus infinity to plus infinity. And so I'm going to assume this and assume that gamma is dilation invariant, so alpha gamma equals gamma. In other words, f of alpha s is the same as alpha times f of s. And so it's convenient to rewrite that formula to understand a little bit better what's going on. And yeah, so if I just introduce a new function g of sigma, which is just defined as so just defined as f of alpha to the power sigma over alpha to the power sigma for sigma in R. Then for this new function, if I look at what g of sigma plus 1 is, so obviously I get sigma plus 1 here over alpha to the sigma. But then we've got this property here that f of alpha s is the same as alpha times f of s.
Don't you need sigma plus 1 downstairs as well?
Yeah, we do. Thank you. So this is the same as alpha times f of, I should write that in. So alpha times f of alpha to the sigma over alpha to the sigma plus 1. And then that's the same as, just the same as g of sigma. So this function g, defined in terms of f in this way is, and if I take any sigma in R, and if I put I'll write sigma as log to the power alpha of s for some s bigger than 0, then g of sigma will be g log alpha s. And sticking that in here, we'll just get f of s over s. So of course that means that f of s in terms of this function g is just s times g of sigma, so s times g of log alpha s. That's a kind of helpful way to rewrite things. So this formula is equivalent to f of s being s times g log alpha s, where the function g is Lipschitz continuous and one periodic. And this is a particular example where g of sigma is sine squared pi sigma alpha equals third, and this is the so this is the half graph gamma. Okay, and so I want to calculate the spectrum of D, the double layer operator on this wiggly graphs like this. The integration in D is integration with respect to surface measure, but just trivially doing a parameterizing the this infinite curve just in terms of distance along the x-axis. Then the spectrum of D is the same as the spectrum of D hat, where D hat, we just replace the integration with respect to surface measure. This is just integral now from 0 to infinity. And this is the particular kernel given explicitly in terms of the function f. And then if I do another substitution, and it's basically just to do this substitution here, relating s and t in terms of some new functions, sigma and tau. So that replaces this property by this periodicity property of G. So this is just another substitution, and the spectrum of D is now the spectrum of this D tilde, where D tilde is now an integral operator on minus infinity to plus infinity. I've got a new kernel kappa sigma tau. I've just replaced S and T by alpha to the sigma, alpha to the tau, and there's a component there coming in from the change of variables. Okay, and the attraction of this is that, which is inherited from the periodicity of this function G, that we have a periodicity of this kappa. And that suggests to us to use a Floquet block transform to understand the spectrum of this operator D tilde. Okay, so just to kind of sum up a little bit, so we've got a G that's Lipschitz continuous one periodic. Our gamma is this with F given in terms of the function G by this formula, and applying the Floquet block transform spectrum of D, we can write it as union over sorry, there's a spectrum missing here. It should say spectrum of dt, union of spectrum of dt over an interval of t between 0 and 2 pi. So this dt, it's the same as the operator that we had on the previous page with the same kernel, but now just integrating from 0 to 1. Yeah, I say the same kernel, not the same kernel. The kernel is kappa t sigma comma t, which is an infinite sum of the original kernel multiplied by some prefactors which depend on t. Okay. So and if G is C2, then this KT kernel is continuous, and we can approximate this integral operator by some numerical quadrature. And in fact, I'm going to do computations for cases when G is real analytic, and then this KT kernel is real analytic. And then just the very simplest numerical integration approximation by the trapezoidal rule is exponentially convergent in that case. Okay, so this is our setup here. I'm assuming now that G is real analytic and one periodic. And an example is this here, sine squared pi sigma. And this is our approximation for the spectrum of D. So the spectrum of D, we're doing approximation for that Floquet block formula that we had on the continuous level. And there's three parameters in the approximation, L, M, and N. The first L is that we're discretizing the continuous interval from 0 to 2 pi. So we're just taking a union of the spectrum of finite grid of points, of L points on the interval 0 to 2 pi. And then there are two further parameters which are to do with approximating the operator dt. And so one of the parameters is that we're doing a very, very simple numerical integration. So approximating the integral from 0 to 1 just by this trivial Riemann sum approximation. But because of the periodicity, this is exponentially convergent, this approximation. And then the other approximation we're doing is the original sum here. The definition of the kernel was from minus infinity to plus infinity. We're placing that by a finite sum from M to M. And so this leaves us with having to calculate the spectrum of this discretized operator. But in fact, it's easy to see that the spectrum of this operator here on C01 is just 0 union the spectrum of this matrix, this n by n matrix, which just has these kind of simple entries here. Okay, so to do the computations, we just compute this matrix, and that's possible to do because we've just got a finite sum here. We work out the spectrum of this matrix, add 0, and this is the spectrum of this, and we take the union over these different values for TL here. Okay, and the nice thing about this is that this then converges to the spectrum of D in the Hausdorff topology as L, M, and N all tend to infinity. And this is a picture for these particular parameter values and showing what this approximation to the essential spectrum looks like in that case. Okay, so I've talked to you briefly about how to calculate approximations to the essential spectrum of to calculate an approximation to the spectrum of D when D is a dilation invariant graph, which then gives you through the localization the essential spectrum of D for the original locally dilation invariant boundary. But how do we know definitively that the spectral radius of D, which is the maximum of this, is really less than a half? Okay, and there are a number of ingredients to that. The first is the numerical integration ingredient, that we have explicit numerical integration error estimates for this simple Riemann sum in the case when the function is periodic. This is in terms of the looking at the magnitude of the analytic continuation. So assuming that psi is analytic and bounded in a strip of width 2c, so going from imaginary part of z minus c to plus c. So this notation here denotes the supremum. So it's analytic and bounded, and also one periodic. And then we have this well-known error estimate for the just this simple Riemann sum approximation. And we see here that it's exponentially convergent as n goes to infinity. And we've captured the constants explicitly. The c is just the width of the strip, and this is just the magnitude of the psi. Okay, and we're applying that to the case where dt is this integral operator, dtn is its approximation. And what we can get is an estimate for, well, not the norm of dt minus dtn, because that never converges to zero as n tends to infinity for any quadrature approximation. But what does tend to zero is the product of that difference multiplied by dt. And so we can get an explicit estimate for that. And in fact, we can compute what these constants c and c dashed are. And we have formulas for those, and those only depend on the width of this strip. Right, and so what's the final ingredient then to proving that the spectral radius is less than a half? So t here is the unit circle, so r naught t is just the circle of radius r naught. And this is the kind of final component that we use. So this is a kind of simple lemma in a general Banach space context. So let me just talk you through this. So the setting is we've got three operators here, which are bounded operators on some Banach space Y. R naught, some positive number. F is some subset of the circle of radius R naught. Okay, and then the conclusion is that the spectral radius of T is less than R naught. And under what conditions is that true? So this is the result for the case when T is compact. And we need to know that the spectral radius of the sig S hat is less than R naught. And that for every lambda on this circle, so there's a picture here. So this is the circle of radius R naught. So here's a typical lambda on this circle. And for every lambda on that circle, there needs to exist a mu, which is in this set F, which is a subset of R naught T. And we need to, for each lambda, we need to be able to find a mu in this subset such that this norm of T minus S times T is less than R naught times the norm of this resolvent to the power minus 1 minus the norm of S minus S hat minus mod lambda minus mu. Okay, and let me just talk through when you might think of applying that. So the idea is we want to show that the spectral radius of T is less than R naught. And the idea is S is some approximation to T. And then S hat is some further approximation by some additional numerical approximations to S. And the idea is to take F to be a finite set, which needs to be sufficiently dense on the unit circle so that you can find for every lambda you can find a mu such that this is true. And then we're going to apply that in our application where T is our operator dt, S is the numerical integration approximation to that. And then S hat is a further approximation to that by two extra things that we're not computing for every t, we're only computing on a grid. So replacing t by some nearby point TL. And this M here means that we've replaced the infinite sum defining the kernel of this by a sum from minus M to M. So as long as we have a fine enough grid, we can ensure and as long as we take M big enough, we can ensure that this is small. As long as we take the finite set F dense enough on the circle, we can ensure that this is small enough. And so then it's just a question of making sure that this here is less than the norm of this resolvent to the power minus 1. So to apply this, we need the explicit band that I just talked about that we get by numerical integration on this norm here, which in our case is this. And helpfully, this tends to 0. We've seen from our norm that this tends to 0 as n tends to infinity. So we can make this as small as we want by letting n tend to infinity. We need also to get an explicit band on this difference. And then to do the computation, we need to be able to calculate these norms here. But in our application, this will just boil down to calculating norms of inverses of finite matrices. And so I thought I'd say something about kind of where this where this lemma comes from to finish off. Let me just get rid of this. So it depends on two auxiliary lemmas, and the first of these, yeah.
Could you remind what is F? Mu belongs to F.
So F is some subset of R naught times T, and in applications, the idea is that F will just be a finite, will be from finite set, which is sufficiently dense on the boundary, so that for any lambda on the circle, you can find a mu, which keeps this small enough.
So F is given. I mean, within this lemma, F is given from the beginning.
So obviously you can yeah. So you can make a choice of F.
Okay.
Yeah. And once you've chosen F, then these conditions have to be satisfied, which involve F here. Okay, so the proof of this just depends on a couple of lemmas. The first of these is just a standard operator perturbation result. Obviously, if A is invertible and C is sufficiently close to A, then C is sufficiently close to A, then also C is invertible, and we have this estimate here for the size of the resolvent norm of C in terms of the size of the resolvent norm of A and the difference, the perturbation. So this is just a standard perturbation estimate. So this is also a standard, an old result. This kind of arises, this condition on looking at a norm of T minus S times T arises naturally when you study approximations by numerical integration. So it's never the case that the norm of dt minus d2n tends to 0, but what is true is that if you T multiply by dt, and the reason for that, of course, is that this converges pointwise as n tends to infinity, and then this maps bounded sets to compact sets. And so pointwise convergence, of course, is uniform on compact sets. So then you get that this tends to 0 as n tends to infinity. And this is this was stuff which was worked out in the 70s under one of the brand names was to talk about collectively compact operator theory. So it's a lovely book from the late 70s by Bill Anselon, for example, with that title. Right, so the second lemma then is an old lemma, but a little bit less familiar. If S and T are bounded operators, T is compact. Lambda is not in the spectrum of S, and T is close enough to S in this sense, then also lambda is not in the spectrum of T. Okay, so these are kind of standard and old results. So let me just look at the proof of this lemma. And so if mod lambda equals R naught, so there's this condition that I've labeled here. So this is one of our assumptions of this lemma, is that this holds, this star holds. But some U in F. And then applying. It's entirely appropriate to call this a lemma. This proof is going to be very straightforward. So applying lemma A with I'm applying it in the case that A is S hat minus lambda I, and the C is the same. Sorry, I mean mu I here, and C is S hat minus lambda I. So that tells us that S hat minus mu I minus 1 all to the power minus 1 minus the norm of A minus C, but of course the norm of A minus C is just lambda minus mu. That's equal to S hat minus lambda I, so minus 1. Okay, and then comparing that to this formula here, so this is the S hat minus mu I, so minus 1 all to the power minus 1 minus the mod lambda minus u. So that's less than or equal to this. So that tells us that T minus S times T, the norm of that, less than or equal to R naught. So I'm just replacing this here by this. Okay, so we got this true for mod lambda equals R naught. But now, because one of our assumptions in this lemma is that the spectral radius of this S hat is less than R naught. So of course, that means that the mapping from lambda onto the resolvent, of course, that means that this is holomorphic. Okay. So of course that gives us from the maximum principle, and also of course this tends to 0 as lambda tends to infinity. So we get that the supremum of this is less than or equal to its maximum. a label with this with a cross then. So so this holds not just for mod lambda equals R naught, but for mod lambda greater than or equal to R naught. So this has its maximum on mod lambda equals R naught. So when we take it to the power -1, it has its minimum on mod lambda equals R naught. So if this holds when mod lambda is equal to R naught, it holds for mod lambda greater than or equal to R naught. And we're just finished by applying lemma B. Lemma B is this lemma here. So we're applying this lemma. So the mod lambda here is R naught. Yeah, so, sorry, so first of all, there's a further application of lemma A. First of all, which enables us to bound this in terms of norm S minus lambda I to -1 all to -1 by applying lemma A, and this is for mod lambda equal to R naught, and then we apply lemma B to conclude that lambda is not in the spectrum of T for mod lambda greater than or equal to R naught. Okay. Yeah. So just to kind of summarize here, so I've presented a method for calculating the essential spectrum of this Neumann Poincaré operator, proving that the spectral radius is less than or equal to half on domains that are piecewise analytic and locally dilation invariant. And this picture is an example, and this is an example of the computed essential spectrum. And the components of that were the localization, first of all, which reduces it to considering locally dilation invariant graphs, Flocky transform, Nystrom method, numerical integration method based on trapezoidal rule, explicit error estimates, and an explicit Banach-based criterion for the radius of an operator, spectral radius of an operator being less than R naught when it's compact. And the computations required to compute these graphs, we need to do eigenvalue computations for lots of matrices, and to get the rigorous bounds on R D naught, we also have to compute these norms here, which involve computing norms of infinity norms of matrices to get those rigorous bounds. And so we haven't disproved this Koenig conjecture as we planned and hoped to do, but we have provided additional evidence that it's true.
Questions?
Did this convince you that it's actually true, or you still believe you can disprove it in some other way?
So we think it's probably true now, and in fact, Siavash sitting next to you, he's working on his PhD student with us, just sort of finishing his first year with us. He's working on a number of spectral theory things. He will talk about something slightly different on Friday. But one of the things he's trying to do is to prove the conjecture is true now. But of course, that's a tall order, because this has been a conjecture which has been around for a while, and obviously some clever people have thought about it.
All the examples that you've shown us where you try to get these problems, the failure of smoothness is really at a or a finite number of points.
Yes, yes.
But I mean, in normally from how I know, when Lipschitz domain are bad is when you have failure of Lipschitzness, failure of smoothness everywhere, somehow, that your thing is just differentiable almost everywhere, but that there's no points of C1. Have you
Yeah, so,
why do you not expect that this would be where the
yeah, I mean, it's got to be depend on the size of the Lipschitz constant as well.
Yeah.
So, because we already know that the conjecture is true when the Lipschitz constant is small enough. Though that's not kind of quantified in terms of how small is necessary.
Yeah.
Yeah, I mean, you could be right, and perhaps there are other more pathological examples one could look at. In the hope of disproving the conjecture. I mean, this is one class of problems where the geometry is pretty complicated, the boundary is pretty complicated, but it's not so complicated that there aren't methods that we can use to actually do computations. And so for a general Lipschitz boundary, I don't have an idea of how one could how one could do computations and especially because there's quite a lot of computation here, but one of the things which saves you is the is the fact that you've got this obviously this graph is quite singular here, but it has this nice structure that it's represented in terms of this analytic function G. And that then leads into all this periodicity and leads into exponential convergence in numerical quadrature rule.
Yeah, I mean, in a way, it seems too nice. Is my point, I guess.
So
I agree with you that it helps to compute the things, but
yeah. But I think this is the nastiest domain for which computations have been done.
yeah,
So
sure,
lots of
sure.
people have done really rather rigorous computations. But it's been for polyhedra and for polygons is the worst that people have gone to so far. And this is a substantial kind of taking things a substantial step further.